probably one near where you live. So tonight we have two great speakers. We have a lot of cool designs for more merch that we would like to get, so please head on over and check it out. It's really awesome. It's a lot of fun. Well, we are having an active example right now, but we are next to an active train line, which means that pretty much guaranteed a train will interrupt our speakers. So while the train whistle, what do we do, guys? Raise our beer, toast the train, and say choo-choo! Yeah, and let's see, what else? During each of the talks, there will be a trivia question. When prompted, please raise your hand if you think you know the answer, and if you get the answer right, you could win a cool prize. My name is Logan Pierce. I'll be your host for the evening. I'm a graduate student here at the University of Arizona, and I'm excited to share the evening with you. So, without further ado, I would like to introduce my peer, fellow graduate student and SpaceDrafts organizer, Soleil Hyman, who is going to tell us about sonification in astronomy. Give her a big hand.
Hi everybody, thanks so much for coming tonight. So yes, thanks Logan for that great introduction, and as she mentioned, I'm going to be talking about sonification in astronomy, and so the title of my talk is Ears to the Sky, and you might wonder why I've got that topic when I've got, hopefully, one second. How's it going? I'm supposed to point this at the laptop, and it's being cantankerous. What? Okay, technical difficulties. Hang on, everybody.
It's not going? Let's just do that. Yeah, try now.
It is scrolling the PowerPoint
Try it now.
instead of
I don't know what's going on. Try now. There we go.
Right, there we go.
On the window. I don't know.
So yeah, so you might be wondering why I'm talking about sound in astronomy and ears to the sky when I've got a beautiful picture of the Whirlpool Galaxy up here. And, well, first of all, in astronomy we typically do represent everything as images, but when you think about it, oh goodness, okay. What our eyes can see is only a very, very small portion of the entire electromagnetic spectrum, which is what makes up light. And what light actually is goes all the way from radio waves, which you can hear on your car radio, if people still use those anymore, all the way to X-rays and gamma rays in your dentist's office and, nuclear reactors and stuff. And it gives us a much larger idea of what space is. And so you can kind of think about using a magnifying glass to study an elephant. Kind of what we have for visible light. We can only see a tiny, tiny portion, but when we look at everything, we can actually see the whole elephant. And so just take one example of that, the Crab supernova remnant, the Crab Nebula. This image up here is a picture from the Hubble Space Telescope. It's something very similar to what our eyes are sensitive to. But if we move into the infrared with the Spitzer Space Telescope, we have a very, very different picture. So it might be a little bit hard to see in the back, but basically the Hubble detail in the middle, and then the Spitzer picture is kind of just nebulous clouds that there's not a lot of detail and definition there. And then if you go all the way to the very high end of the light energy, so go to X-rays, We've got, with the Chandra Space Telescope, or Chandra X-ray Observatory, we've got the actual pulsar wind nebula of the Crab Nebula. And if you combine those pictures, we get something like what we see in those beautiful press releases, those multicolor composite images that give us a larger picture that's greater than the sum of its parts. And so this is kind of one overview of astronomy and how we visualize things, but what if you can't see? I'm going to put this up, and this may look familiar to people. It's an image of the sun in the totality portion of a total solar eclipse. We see the gorgeous corona. All right, I'm going to train coming. I'll try to make it before it comes. All right. No, I'm going to wait because I have some sound to play. Good timing. Enjoy the couple-second intermission while the train comes by. Choo-choo.
I have a bad feeling this one might be when it stops.
Seems like this might be the Amtrak. Nope, I'm wrong. UP.
I'll post up by the volume knob in case you need to hear more volume. All right, can we try now?
All right, let's try this now. So yes, as I was saying, beautiful image of totality portion of a solar eclipse, but what if you can't see? How do you experience a solar eclipse? And so I want you to close your eyes for a minute, and hopefully you'll be able to hear this if the train's not too loud. Can you turn it up?
Yeah.
Okay, hang on.
Oh, I hear it. It's coming out of my speakers still. What the
Okay.
heck? Hold on. One
Technical
second.
difficulties again. We're getting some sound from the computer speakers.
Every dang time. Can you go back and forward again? Oh, it's not. Okay. There we go.
All right, there we go. So can everyone hear these clicks? So these clicks that you're hearing are, as they're slowing down, is an actual sonification, which is converting some sort of data or signal into sound as the day gets darker and darker during the totality of a solar eclipse. And this is part of a device I've been involved in developing, which is called Light Sound, and it's a device for making solar eclipses more accessible to blind and low vision individuals. And this is important, especially with the 2017 eclipse came right across the United States. We've got some upcoming eclipses that are going through a lot more very populated areas, and we want these to be accessible to people to actually be able to enjoy and be inspired like everyone else. And so it's not only just good for people who can't see or have difficulty seeing. It also is really cool if you can see as well, and it can be useful if it's cloudy and you can't see the sun, or if you can't safely look at the sun without eye protection. And so yeah, so this is an example of what I called sonification, and some of you might not have heard what this is before, so just put a quick definition up. Goodness, this is going to drive me crazy.
It is. Okay, we're patient.
Thank you.
There you go.
All right. Yeah, so sonification is using nonverbal sound, so non-spoken sound, to convey information or describe data or signals. And so you might wonder, how does a device like Light Sound work? Well, you've got the light coming from the sun, and it reaches the device that you have pointing at the sky, and there's a sensor in the device that takes that data that it records how bright it is, the light intensity, and sends it to a microprocessor, which is kind of like an onboard computer. And from there, it sends that to a MIDI board, which tells what instrument to play. And depending on how bright the light is, we have 4 different sounds. So for very dark light, you heard the clicking before, like that. You have a clarinet for kind of indoor medium light. a flute for very bright light, and a plucked string for saturated light. But that's not the only thing you can do, and you can record the data and plot it like you might do in a science class. Fifth time's a charm. Come on. Cute.
I can try to advance it.
Yeah, can you try that, Lily? All right, thanks. And yeah, so you can plot it, but then you can also take those devices that you've had across the country. And so this particular plot actually is from the 2019 South American solar eclipses in Chile and Argentina. And so we developed, we built 20 of these devices and spread them across the path of totality in these countries to make them more accessible to blind and low vision people. And then we actually took the data from that and turned that into a map. Push it again. And so what you're hearing is the sound of 4 different locations in Chile and Argentina as they sonify the eclipse. Now, you can watch as the shadow passes across the continent, and you can hear the totality happen. All right, so that was one way you can sonify the shadow of the sun, or the shadow of the moon from the sun, passing across the surface of the Earth as seen from 4 different locations in South America during an eclipse. But sonification itself is not exactly a new tool, even though it's becoming much more popular nowadays as for research and for also public outreach. And it's actually been around for a while. So play a little game. What do these 2 things have in common? So you've got the Green Bank radio telescope, and then you also have this sound recording. So sounds like radio static? Well, it is, but it's not just that. It is actually the sound of the cosmic microwave background, which is leftover radiation from the Big Bang, and that recording is actually courtesy of one of the people who discovered it. And the way they discovered it was not for an astronomy project. It was actually 2 guys at Bell Labs in New Jersey, Bob Wilson and Arnold Penzias, and they were studying transatlantic satellite communication, this crazy idea of having these satellite balloons in the atmosphere that you could bounce radio waves off of and communicate really long distances. And they were using this crazy-looking radio horn. It's called the CMB horn now. And they kept hearing this white noise that they couldn't figure out where it was coming from. They did a bunch of tests, and eventually they realized that it was actually leftover radiation from the Big Bang, which is now today called the cosmic microwave background. And that's not the only type of sonification, type of discovery that's been made from sonification. In the 1930s, so a couple decades earlier, Carl Jansky, who's now considered the father of modern radio astronomy, was also an employee at Bell Labs, and he had this crazy-looking radio antenna, which people called like Jansky's merry-go-round because you could move it around. And he kept noticing that there was this radio source near the sun, and so he was tracking it. He figured maybe it's radio emission from the sun, which does happen. But he noticed that day by day it started moving a little bit more, and it turned out it was actually the center of the galaxy. So the black hole at the center of our galaxy, and it was a very active radio source. And that emission was actually coming, that was the first detection of radio source outside of our solar system. And so it's kind of cool. You think about the Green Bank radio telescope, and this was actually the world's first radio telescope. And you can see how much things have changed since then. So just a couple other examples of sonification. In the 80s, actually, when Voyager was passing through the rings of Saturn, they were trying to figure out what was going on with some of the signals received from the spacecraft, and they were looking at visual outputs of it, and it just looked like noise, but when they actually listened to it, they heard this kind of rapid fire hitting, these pops, and it turned out that it was actually micrometeoroid strikes striking the spacecraft, but it was just noise to our eye, but you could actually hear it. And that's one of the beauties of sonification, is that our ears are much better at picking out noise from, picking out a signal from noise compared to our eyes. You can think of, if you're standing in a loud room, you can understand a conversation, you can hear a nearby conversation and eavesdrop a little bit. But if you're trying to find someone in the room, it can be really hard if there are a lot of people. Another more recent example from the early 2000s was with the NASA ACE, Advanced Composition Explorer, studying properties of the solar wind, and they were actually able to understand the presence of different carbon ions, so different charged types of carbon, charged atoms, whether they were present by listening to sonifications and the presence of various harmonics of this compared to some fundamental pitch. So there's a cool kind of overlap between music and the arts and science, and I think that's one of the really cool things about sonification itself. Another example that some of you might be a little bit more familiar with is the announcement of gravitational waves back in 2016, and so this is LIGO, a laser interferometric gravitational wave observatory, and they're measuring how space gets distorted based on Einstein's theory of general relativity. And one of the things that kind of got popularized from this are these chirps that you might remember. And so it sounds very simple, but it actually is a very very elegant way of representing this kind of complex way of visualizing data, and through simplifying it kind of through sound. So yeah, sonification is a very powerful tool in astronomy, and it's also being worked into being used as more active research, and that's kind of an ongoing thing. But yeah, so some trivia time now. We're going to test your ears with some sonification. All right, so I've got 4 plots up here, and I'm going to play a sound recording and then have people raise your hands and see which plot matches the correct which is the correct plot for the sound. All right. 4? That is correct. So good job, and come up after the talk and get your prize. So that was kind of an easier one. This next one is going to be a little bit more challenging. So this is kind of a simulated exoplanet transit. So the light of the star is dimming as the planet passes in front of the star. And so it's very noisy, but you actually will be able to hear, tell the difference between these 4 recordings. So I'm going to play the 4 recordings and then see who can correctly identify the right recording. All right. I think I saw your hand first. That is correct. So good job. Good ears. That's a little bit trickier. All right. And so just kind of looking at the future of what I've been doing in sonification, as I mentioned at the beginning, we've got eclipses coming up in 2023 and 2024. There's actually an annular that's passing not too far from us in northeastern Arizona, New Mexico, Nevada, Utah areas. just about a year from now, a couple days ago, as of a couple days ago, and that's an annular solar eclipse, which is sometimes called the Ring of Fire eclipse. The moon doesn't completely cover the disk of the sun, and so you can't look at it safely with your naked eye. You can do so with proper eye protection, but you see this beautiful kind of fiery ring around the dark disk of the moon. And then there's another total eclipse coming up in April 2024. That's going from Texas up through New England. And we've been trying to build a bunch of these devices and try to distribute over 100 of them across the paths of the eclipses to make them more accessible to the blind and low vision populations in the United States and also Canada. And yeah, hopefully if you're at any of these eclipse events, you might even see some of these light sounds. And if anyone's interested in using them, I would love to talk, and please get in touch with me. But yeah, and some other steps towards making astronomy more accessible in terms of teaching. We've got the light sound, as I mentioned, but then we've also been developing another device which we call Orchestar, which is taking color and turning it into sound. And that's really important because in astronomy, there's a strong relation between color and temperature in terms of how hot things are, the bluer they are, and that actually sonifies color with pitch, and that has a good relation to light and temperature. And so that's kind of my very fast overview of sonification and astronomy. There's lots more to talk about, lots of cool things being done with it. But I'll be happy to take any questions, and I'd also like to leave you guys with a question, which is, what's the next frontier of sound in space? Thank you. Yes.
It sounded like you were part of a large team. Can you tell us more about who you're working with?
Yes, that is a great question. So the question was, it sounds like I'm part of a large team and who I'm working with. So the concept of the light sound was actually was conceptualized by the astronomer Wanda Diaz-Merced, and she's actually a blind astronomer. She does amazing work, and she's a trailblazer with making astronomy more accessible and also making astronomy research more respected with using sonification, because it's still not a super familiar tool for a lot of us, and that's been a problem with making it more commonly used. And she wanted to make this eclipses accessible for people and for kids to get inspired and excited about astronomy. And so she was kind of the genesis. She came up with this idea, and then I've been working with Alison Barilla at Harvard University. So I started this as my undergrad, as part of my undergrad research and outreach, and I've been working on this since. So. All right. Oh, yes.
What got you into this? Like, I've never heard of sound in space really more than just a concept. So what excited you to study this?
Yes, the question was what got me excited about this. I'm also a musician on the side, and I play trumpet. And so when I heard about this project, I got very excited and kind of combining those two things. So. Cool. All right.
Let's give Sully a round of applause. All right. It is 7:56. So let's take a 20-minute intermission. So we'll see you back here at, let's say, 8:15. And during your intermission, please feel free to refresh your beverages, tip your bartenders, and also don't forget we have our lovely astronomy club students out here very excited to show you what's up in the sky. So see you back here at 8:15.
Know how to do that without massive feedback. I put all of the slides into one slideshow so you can just advance.
I don't understand why it was half
Yeah.
working and half not.
Was
What was half working? Oh, the
Pointer.
so was the
maybe like this needs to.
like two versions of the same slideshow, right?
I was not touching it
Okay.
in between times that worked and times that didn't.
Okay.
Yeah.
So I don't know.
Oh, there's 8 people on.
Do we want to test it?
So I don't know what to do other than just like me keep an eye on the speaker, and if it's not going, then go.
Since
It took me so long to figure that out.
Is this the clicker?
All right, it is 8:15, so let's come on back from intermission. Hope you enjoyed seeing Jupiter and I saw 4 Galilean moons around Jupiter, which is always just so cool to see. I love seeing that. Even though this is my everyday job, it just fills me with just such excitement to see the 4 Galilean moons with my own eyes. And on that note about backyard observing, next up we have Jim Knoll from the Tucson Amateur Astronomy Association to tell us about what's up in the sky right now and what kind of events they have going on this quarter. So please give him a round of applause.
Thanks, Logan. Yeah, so if you haven't had a chance to go out and look through the telescopes, you definitely want to do that, because 2 of my most favorite things to look at through telescopes are Jupiter and Saturn, and they're both visible and they look awesome in the telescopes. And we're going to talk about them a little bit tonight. So with that in mind, before we get started, let's just have a little review of the solar system and where we live, just in case anybody forgot. So we got the 4 inner planets. They're the rocky planets. So you've got Mercury, Venus, Earth, and Mars. And then in between Mars and Jupiter, we have what's called the asteroid belt. And that is where, and thanks to Jupiter's gravity, that helps to keep that belt in place so that we don't have a lot of asteroids coming into the inner solar system. And then we've got the 4 gas giant planets. So you got Jupiter, Saturn, Uranus, and Neptune. And all 4 of those planets are visible tonight. And we'll talk a little bit about that. And then way out in the outer solar system, you got little old Pluto hanging out there. Pluto is the beginning of what's called the Kuiper Belt. And the Kuiper Belt is where we have some of the short period comets and some of the asteroids that will zip in, like Halley's Comet, and some of those that will come into the inner solar system every few years. And then beyond the Kuiper Belt, we have what's called the Oort cloud. And the Oort cloud goes almost halfway out to the next star system. So Proxima Centauri and the Alpha Centauri system is the closest star system to us. And it's 4.2 light years away. So the Oort cloud goes almost about 2 light years out. And that's where you'll have some of the long period comets, the ones that maybe take thousands of years to come into the inner solar system and go back out, and things like that. So with that in mind, let's go ahead and let's talk first about Jupiter. Jupiter just went through an opposition in September 26th. And what that means is that when the outer planets are opposite the sun from the Earth, that's when they become opposition. So, you know, you've got the sun and the Earth, and the planet is just outside and in a straight line from the sun and the Earth. And that's when they're the closest to Earth. And so in Jupiter's case, it was actually the closest to Earth since the last 59 years. So it's been 59 years since it's been any closer. And it was only 367 million miles away, and it's now about 376 million miles. But just that little bit can make a difference in being able to observe the details. So when you look through a telescope at Jupiter, even the scope's out here, you'll see the 2 cloud bands going through the middle. Let's see, I think this has a pointer.
It's the red button.
Top.
It's like a red.
There it is. So you see the 2 cloud bands going through. And then, like Logan said, you can see up to 4 of the Galilean moons, and I think they're all 4 visible tonight. Sometimes the moons will go behind the planet, or they'll do a transit across the face of the planet, so you may not always see all 4 of them. But they'll always be lined up right across the equator, just like our moon orbits around our equator. The moons of Jupiter in particular are pretty much lined up, the 4 we can see. Now, Jupiter has 79 moons. So it's got quite a few. Basically, anything that gets close to Jupiter either crashes into it or becomes a moon. So definitely take a look at that. And then Saturn is just absolutely awesome in the telescope. You can see the rings. I get a lot of comments when I show people Saturn for the first time. They think it's a sticker, a picture. is because it does. It really looks like a picture. And you can clearly see the rings. You can usually see 3 to 4 of the moons. And so, and Saturn actually has, it's about half the size of Jupiter, but it actually has more moons than Jupiter does. And it's another 400 or 500 million miles further away. So yeah, Saturn's got 82 moons, and Saturn actually takes about 30 years to make one revolution around the sun. So ours is 365 days. Saturn doesn't move very fast. It's pretty slow. And then Neptune, oops, I think I skipped one. Uranus and Neptune kind of look the same in the telescope. They'll look like tiny little blue dots, but when you look at them, you can, if you imagine, you can put up to 60 Earths inside those tiny little blue dot. So if you were out at Saturn or out at Uranus or Neptune trying to look back at the Earth, think about this, you know, I mean, the Earth is so much smaller than these guys are. It would be very, very difficult to spot it against the backdrop of the sun and the inner solar system. And something really bad happened to, let's see if I can go back, to Uranus in its early days, and it actually orbits on its side. It's got about a 98, I think it's a 98 degree tilt. So something knocked it on its side, and it actually orbits on its side. Uranus takes about 84 Earth years to make one orbit. And then Neptune is another billion miles away, and it takes 165 years to make an orbit. So these guys don't move very much in the night sky. So all 4 of those planets are visible tonight. Mars was also visible. It should be coming up probably right about now. It'll look like a reddish orange orbit or a circle in the telescope. And if you've got some pretty decent skies and a decent telescope, you can actually see the polar ice cap sometimes. And Mars is obviously one that we've visited an awful lot. We've done a lot of missions to it. And it's about half the size of Earth, and it takes about twice as long to orbit the sun as the Earth does. And it has 2 moons. And finally, Venus. Venus, a lot of times you'll hear Venus referred to as the morning or evening star. And it's not a star, obviously, but it never strays very far from the sun. So it's always going to be either in the morning sky in the east or in the evening sky in the west. And it's bright. I mean, it's really, really bright. Sometimes it gets confused as a UFO or an airplane or something like that because it almost takes on a 3-dimensional look. Venus is sometimes considered to be our twin, but that's in size only. The surface of Venus is more than 800 degrees Fahrenheit, so it's not a good place to be. It's got a runaway greenhouse gas effect, so it's enshrouded in clouds. But they are talking about doing some missions to Venus to be able to study the clouds a little bit better. All right, and then we've got some deep sky objects, and I think they were planning on looking at a few of these tonight in the telescopes. We actually have the Andromeda Galaxy is visible tonight. That's M31, and it's 2 satellite galaxies, M32 and M110. So when you look at the Andromeda Galaxy, you're looking at 2.5 million light years away. So you're looking back in time 2.5 million years. And you can actually see the satellite galaxies, the smaller galaxies of the Andromeda Galaxy. And Andromeda is the furthest object you can see with your naked eye from a dark site. So you got to get out of the city, but you can actually see it. You can see a little hazy spot in the night sky, and it's 2.5 million light years away. The other big galaxy that's out there as well is the Triangulum Galaxy. That's M33. It's actually a satellite galaxy of Andromeda. It's another couple 100,000 light years further away. So between Andromeda, Triangulum, and the Milky Way, those are the 3 big galaxies in our little local group of galaxies. And we all have little satellite galaxies, companion galaxies with us. And over the next 4 to 5 billion years, we're going to be slowly drifting together. And we'll become one large galaxy. So you can actually see the Andromeda Galaxy fairly easily in a telescope. We've also got some really cool open clusters. The Pleiades is probably right up about there. And I guess it is just coming up, isn't it? And Pleiades is also known as the Seven Sisters, and it's an open cluster. And in Japan, it's called the Subaru cluster. And it's actually the pattern of the Subaru car logo minus 1 star. It's just got 6 stars, but it's the same kind of pattern. And then the double cluster in Perseus is pretty cool to look at in telescopes. And then the owl cluster actually kind of looks like an owl or an ET. A lot of times it's called the ET cluster. So those are really good clusters to look at in telescopes. I know that the guys back there were talking about maybe looking at Albireo or Polaris, some double stars. Polaris, our North Star, you can actually see the small companion star associated with the North Star. So you can see 2 stars in a telescope. And same with Albireo, which is pretty much straight up, and that's the head of Cygnus the Swan. And that one is a really nice looking double star. You can see it's an orange or a yellow giant and a blue dwarf. So you can see the yellow and the blue color differences between the two. And then Mizar is kind of low in the handle of the Big Dipper. That's actually a 4-star system. So Mizar A and B are 2 stars, and each one of those stars has another star we can't see, so it's a 4-star system. So if you were on a planet around one of those stars, you'd have 4 suns. And then in Alcor is the other one that you can see naked eye near Mizar. And then there's globular clusters like the Hercules cluster, which is some of the older stars in our Milky Way galaxy. They're 9 to 12 billion years old. And the Hercules cluster really looks nice in a telescope. And you can see hundreds of thousands of stars just clustered together. So like I said earlier, the nearest star to our sun is Proxima Centauri, which is 4.2 light years away. The average distance between stars in something like the Hercules cluster is 0.1 light year. So you would have stars filling the night sky. And so it'd be like almost like daytime. And then nebula is kind of cool to look at as well. The Ring Nebula is the gas that's coming off of a star that's going through it's used up all of its hydrogen, and it's in its death throes. It's in its final stages of becoming a white dwarf. And that's what's going to happen to our sun in about 5 billion years. It'll look something like the Ring Nebula. It'll start puffing off its gas. So when you look at the Ring Nebula in the telescope, you see what we call a donut or a Cheerio or a little circle of gas, and that's the gas coming off the nebula. So the Ring Nebula and the Dumbbell Nebula are stars that are at the end of their life. And then there's a lot of nebulas like the Orion Nebula and nebulas that are in the Sagittarius constellation that are stars that are being born. So you can see both ends of the spectrum there. We also have 3 great meteor showers taking place. The Orionids are active right now, and they peak this weekend. So most meteor showers, you actually want to be able to, you want to look at them in the early morning hours, because if you think about like when you're driving into a rainstorm, you can more prominently see the raindrops hitting your front windshield than you can the back. Well, the same thing is true with meteor showers. Typically, from our perspective, when we're plowing into the meteor shower, it's in the early morning hours. And so we're going to be able to see more of the brighter, more prominent meteors than you would if you tried to observe it in the evening when we're not plowing into it. So the Orionids are going on right now, so if you get a chance, it's not a real big meteor shower. You can see maybe 10 to 20 meteors that are, if you get out in a dark site. And then in November is the Leonids, and that peaks in the 17th and 18th. Again, not a real strong one. The Orionids going on now are, we're plowing through the debris stream from previous visits of Halley's Comet. And the Leonids is from Comet Tempel-Tuttle. And then probably the most prominent meteor shower is the Geminids, and that's in December. And that one is usually pretty good, but unfortunately this year we're going to have a really bright moon, so it's going to be really tough to see some of the fainter ones. But if you get an opportunity, that one peaks December 13th and 14th. If you can get outside the city and try to take a look at some of those will be pretty good. So those are the 3 that are coming up. And then finally, I'll just wrap up with some of the star parties and events that we've got going on within the club. So we're doing an event this weekend down at the Chiricahua National Monument if we don't get clouded out. And then the following weekend, we have an astronomy complex that's not too far from the Chiricahua Mountains. And we actually open up the site and do an evening under the stars. And so, you know, if you're interested in coming out and seeing a dark site, that one's really good. We do this one. We do request reservations, but you can get to any of the information on any of these events. You can get to our website and look at the events, or you can go to our Facebook page and look at the event as well. And then next month we have several public star parties to include. We do a quarterly virtual star party, so we actually have 3 or 4 telescopes connected up with cameras, and we'll stream it to our YouTube channel, and we'll show different objects and talk about them, and it's a lot of fun. So that one is going on the 18th, and then we've got some public ones in November and December. And that's it. Any questions? All right, thanks.
Thanks, Jim. All right. And our final speaker of this evening is Veronica Bray. She's going to, from LPL, yeah? Right? LPL?
Yes.
Okay, just from Lunar Planetary Laboratory. And she'll be telling us about killing the dinosaurs. Let's give her a round of applause.
Hi, thank you. So, I'm Veronica. I work at the Lunar and Planetary Laboratory, where I have 2 different jobs. One is as mission operations for the HiRISE camera, taking photos of Mars, and then the other half of my job is as staff scientist. So that's what I'm presenting tonight. I use computer models to recreate the impact of comets and meteors into planetary bodies. And so it's really useful. I can answer very specific questions because I have complete godlike control over whatever's the projectile that's coming in. I can change its impact angle, its speed, whether it's iron or rocky or icy. I can also change the target structure. I can add an ocean, I can add layers. And so usually when I publish my work, it's such a specific question that about 10 people in the entire world are interested at all. And so that's the level of engagement that I'm used to. But a couple of months ago, we released a paper that was a discovery paper. We'd found a new impact crater, so one of the scars of these meteor impacts, and it got a lot more fanfare than I was used to. So the crater that we think we've discovered, and I do specify think because we'll only be able to prove it when we drill down below the seafloor into the rocks, and we'll be able to get some of those shocked rocks back and prove that it's an impact crater. But we think we've found one that's about 9 kilometers across. It's on the Guinea Plateau, which is just off the west coast of Africa. We found it accidentally in seismic data that was for a different project, and the lead author on the study has found this interesting feature in his seismic data and came to me and another scientist and asked, do you think that this is an impact crater? And when we looked at where it was in the rock column, we worked out its rough age. So we can get a rough age from where things are in a column of rocks, because when sediment deposits, it then turns into rock over time, and so your lower levels are your oldest rocks, and the rocks get younger and younger as you go up. And so that's how we determined that we think that this crater is 66 million years old, roughly, which is the same age as the dinosaur killing impact event which caused the Chicxulub crater. And you have there, well, you have the different locations on the globe here of the Chicxulub, CH, on here, impact crater, which is the established dinosaur killer on the Yucatan Peninsula, and our new crater, the Nadir crater, on the Guinea Plateau, marked GP. So it got a lot of interest. I was completely unfamiliar with this level of interest in my work. It was very enjoyable. But a lot of people, they got really excited about the potential age. And so cartoons like this were created. So this is from a Tucson artist called Thaddeus Camp, and it says, "I tell you what, we dodged a bullet," and it was really part of the idea that the dinosaurs were killed by 2 impacts, which technically, yes, technically true, but I realized while I was giving this week-long set of interviews and like on radio and newspapers and having a really honestly good time, that I needed to do Chicxulub justice because it could have done the job on its own. So we're going to go into that. This isn't to downplay our discovery, because we only know of about 200 impact craters on Earth. Earth has got a really active weather system, it's got plate tectonics, so the scars of meteor impacts don't last very long on Earth. So we've found one of the 200-ish impact craters. But Chicxulub really dwarfs the Nadir impact. So we think that the 9-kilometer crater, the Nadir crater, was formed by a 400-meter diameter meteor, whereas the Chicxulub impact was formed by a 14-kilometer one. So this is a completely different level of damage. And it's too big to comprehend, so I wanted to start with something local, something smaller. If you've never been up to Meteor Crater, then you should do. Shame on you. It's right up in Flagstaff, and it is one of the best examples of where we have been hit hard by an object from outer space. If you go up to Flagstaff, you've got the Grand Canyon in one direction, Meteor Crater's just the same distance in the other direction. And it's small enough in terms of an impact crater that you can see how big it is. You can see the visitor center. So this is a whole building and the road coming off here. So you can see that this, what I would describe as a very small impact crater, is a mile wide. And it's deep enough to hide the Statue of Liberty. If we put the Statue of Liberty at the bottom, the torch would not show above the top. And so I've shown the impact energy, the amount of energy released from this impact event. It's the Barringer crater here, which is the official name for Meteor Crater, and compared that to, for example, the Nagasaki nuclear blast. So even what I would describe as a small impact crater dwarfs the nuclear bombs that we have as examples. Going further up, with all of the zeros at the bottom, the Nadir crater dwarfs that still, and then Chicxulub has all of the zeros. It's and I can't comprehend this. It's something. It's meaningless. That many numbers, that many zeros is meaningless. So what I'm presenting you today is the real-world effects of the impact craters. So let's start with that small one, our neighbor, the Barringer meteor crater. It's about 300 kilometers from Tucson to Flagstaff, which is fortunately very similar to the distance from Nadir impact crater and the west coast of Africa. So we can imagine that we are dinosaurs standing on the west coast of Africa when the Nadir impact crater occurs. But for the purposes of demonstration, I'm going to put all of our impact craters in Flagstaff and then tell you what happens to us down in Tucson as a result of them. So when the Barringer meteor crater formed, it was too far away for us to be hit by any of its ejecta. So when that asteroid or the comet plowed into Earth, it formed this impact crater by throwing out all of this rock. We're too far away to have got any of that. We would have received a 2-mile-an-hour wind. So today was windy. It got up to about 16 miles an hour, so you wouldn't have noticed it. Maybe it would have given you a bit of relief on a hot sunny day, you know, a 2-mile-an-hour reprieve. We would have heard a 50 decibel bang, so heavy traffic. You might not have noticed it. If you were talking too loudly, you probably wouldn't notice the bang. the earthquake caused by the Barringer impact would have only been felt down in Tucson if you were at rest. I'm not sure how static and paying attention you need to be to feel that, but yeah, Barringer meteor crater wouldn't have affected us down here at all. Now, if we go to the Nadir impact, so instead of a 50-meter projectile, it's a 400-meter projectile coming in. I've now put a circle over meteor crater because we're now large enough to be seen on the map. And there's going to be a play-by-play for us here in Tucson. 10 seconds after the impact event, we're going to receive the thermal radiation. We're then going to receive the earthquake at about the 1-minute mark. We will get some ejected down here at the 4-minute mark, and then we will receive the air blast. So let's talk about what these mean in terms of effects. So in Tucson, we will see a fireball up near Flagstaff that's 2 times the size of the sun. So it'll be notable if you're looking the right way. We'll only get 1.5 times solar flux for 2 minutes. So we're used to that on a hot Tucson day anyway. So again, it's not very dramatic. The orange area that I've marked on the map here is where you would really need to be concerned if you've got friends and family up in Flagstaff or Sedona. They'll be on fire. But down here in Tucson, we're good. And parked cars will kind of rock on their wheels a little bit. So nothing's getting destroyed down here very much, but it will be a notable event. Again, the green circle that I've added on are for the friends and family up in the north. This will be the partial collapse of structures if they're not well designed. And seriously, what earthquake-ready designed houses do we really have in Arizona? So partial damage to the green area up there. So the next thing we're going to get, 3 minutes after our earthquake, we're going to receive the ejector. I've again put on the bad damage zone in the grey circles. The inner damage zone is where they've been covered in 1 meter depths of rock. You'd have trouble dodging out of the way of this as it comes down on you. And then the lighter grey area is 1 centimeter of rock. And down here in Tucson, we're just going to get a 3 millimeter dusting. So it may be some ashy snow sort of action for us. And then the air blast. The air blast reaches us 15 minutes after the impact event. The blue circles in the middle are the destruction zones. So in the center, metal frame buildings will be blown down, so pretty much leveling that central blue region. And then as you get further away, it's less destructive, so any poorly constructed buildings will be blown down in Scottsdale. But down for us in Tucson, you know, we're still pretty safe. We're going to get a 40-mile-an-hour wind. And like I said, it was windy today. It was 16 miles an hour. So this is a considerable wind gust, but it's not going to knock anyone off their feet. Apart from the fact that I'm giving this talk in a brewery, so maybe at the end of the night, some of us might get knocked off our feet by the blast wave. We'll also get I can't read it from here, a 78 decibel bang. The trains come in at about 110 decibels. So you'd notice it, but it's not going to hurt your ears very, very much. So, if you imagine that mushroom cloud is the Nadir impact crater, it will have killed off some dinosaurs on the west coast of Africa. It will have caused a tsunami as well, because this impact occurred into water, so that's going to kill off a few more dinosaurs on coastal regions further afield. But the big one is the Chicxulub impact. So it's the same play order because we're the same distance, and it takes rock the same amount of time to fly, no matter how big the event is up in Flagstaff. So adding on Chicxulub, this is just the crater. This isn't the ejector, this isn't anything else. So your friends that were on fire in Flagstaff wouldn't need to worry about that with this one. It's going to be quick. And so you get where this is going. From this point on, all of the impact effects are going to be a lot more dramatic for us down in Tucson. I wanted to give you a size of the global effects here, and so I've got Nadir impact crater over on the west coast of Africa there, and the Chicxulub impact crater at its impact location on the Yucatan Peninsula. And this just shows the thermal radiation effects, so that you can get an idea of how much wider reaching the Chicxulub event is. So, in Tucson, we will be able to see the fireball because the fireball will be 120 miles across. Now, previously, the orange zone, I made it to be the clothing ignite zone. But on this, the effects are so large that I've just used it to show you the fireball itself. So all of that area is in fireball. So we would see that in the sky as 125 times larger than the sun. You'd notice it. What you would definitely notice, if you were looking in the wrong direction, I guess, and if you missed the fireball, is 37 minutes of 1,410 times the power of the sun heating you up. This will lead to predictable things like clothing and wood and trees all igniting. You'll be burnt, obviously. And the only... Wow, you have a fast processing computer. This rather... these dramatic videos that move faster than they do on my computer, and it's freaking me out. They're showing you the results of some nuclear tests, which is the best examples that I have to show you what we would be experiencing. The first is an example of the fireball, and then the one at the bottom is, I assume, a school bus that it's not being blown away, but the thermal pulse goes past it and instantly burns it. It just goes past, and yeah. So next, we've got that earthquake to contend with, and here again is the comparison between Nadir crater and Chicxulub crater. Nadir crater was 7.5 on the Richter scale. What we expect from a Chicxulub level impact event is somewhere at 10 or over. We have never, in recorded history, experienced a magnitude 10 earthquake. It's at a level where we would expect the crust not to be able to deal with it. Like the Earth's crust wouldn't be able to deal with this much energy release. The highest that we have in recorded history is from Chile in 1960. That was a 9.5. And San Francisco was a magnitude 8. And so I have a couple of pictures from that complete devastation in Chile, and cracks opening in the road in San Francisco. I tend to play things down descriptively, so I've just summarized this with general panic as one of the effects of a magnitude 10 earthquake. Full-scale building collapse. I don't need to specify the type of building. It's just rubble now. But then, as well as just reducing things to rubble, we have further damage to underground things. The things that we don't think about, our water, our gas lines, all of these things that are suddenly causing us problems and creating fire risks. as if you weren't on fire already, the gas lines would be a problem. We'll also get earthquake fountains, so these cracks in the ground, some of the earth underneath is basically pushed up, creating showers of dirt. So after that, we've got the ejector is incoming. And remember, we didn't have very much ejector at all from Nadir, just 3 millimeters of dust. So the Chicxulub impact ejector will reach us again at the 4-minute mark. Right round the outside of the orange circle, I've got the grey circle. And this is showing you the depth of more than 100-meter rock depth. So anything inside this circle is covered by more than 100 meters worth of rock. Down here in Tucson, it's not quite that bad. We're only going to be covered in 20 meters of rock. So my house will be buried. We can expect this to come to us in an average, not a maximum, but an average of 2-inch particles. Particles that rocks, 2-inch rocks, burying us. And if you've got 20 meters of rock on your roof, it's unlikely to survive. So you will get roofs caving in. But you won't be on fire anymore. My personal favorite, the Chicxulub air blast. You can see how global this was. So, and it's kind of adding insult to Nadir's injury. If the Nadir impact occurred first, you've already gone through your thermal pulse, your earthquake, your ejector, and your own air blast, and then you're going to be getting the Chicxulub air blast as well. Down here in Tucson, it's going to be much more than 40 miles an hour. We have 2,700 miles an hour gust of wind coming at us. Again, glass shatters is one of the I didn't know what else to put, but seriously, if your building's not going to survive this, so you won't really care about your window panes. But also, anything that doesn't have a foundation, a deep foundation, will be blown away. And so, but everything. So it's not just one car heading down out of state. It's all of the cars and everything else that will then be banging into each other, and they will basically meld around each other. You won't have a recognizable car at the end of this. It will just be amorphous blobs of metal. And again, this is very difficult to comprehend, and the only example I have is from nuclear tests. And this is an example of the air blast from a nuclear test, a very short video, because of course, when the blast wave hit the camera, it stopped working. The other example I have here is from the Tunguska air blast event, so this wasn't even an impact. This was just an air blast in the atmosphere, which released enough energy to flatten the trees. While I was trying to find relatable things to try and explain some of these impact effects, I came up with this interesting bit. So remember, with each air blast, we also get that associated loud bang, which was 78 decibels for the Nadir impact crater. Not as loud as the train, which hasn't come around during my talk yet. Don't jinx it. The Chicxulub bang would be louder than that. It would be 130 decibels. We start getting permanent hearing damage at 90. Pain begins at 125 decibels, so if you've walked past road work and they're using the pneumatic drill, that tends to run at about 125 decibels. But hilariously, KISS in their 2009 tour actually clocked in at 137 decibels. And there are reports of masonry falling off the stadium. That's what would happen to us down in Tucson. but we're just one area. So I wanted to finish off the talk by giving the global consequences. The global consequence from Nadir impact crater, not very much. Like I said, it's going to kill some dinosaurs on West Africa, but that's about it. You might get some ejecta and some vaporized rock enter the atmosphere, but it won't affect us significantly. Chicxulub, however, a lot of the ejecta that got thrown out will have reached so high into our atmosphere on ballistic trajectories that as it starts turning around and re-entering the atmosphere, it heats up because of... I did jinx it. It's somewhere between 96 and 110 decibels. Well, I'll talk in between the blasts. So the ejecta comes back in through the atmosphere and heats up because of the friction with the air molecules. And so it's basically a rain of fire. And when this incoming ejecta hits the ground, it's on fire, so it sets fire to the globe. This video up the top here is showing the wildfires spreading across the globe over time as this ejecta comes back in. But also, the atmosphere itself gets heated up by this process, and so it kind of superheats our atmosphere and creates oven-like conditions on the surface for hours. So, Venus surface-like conditions for a few hours. The ejected dust will block out the sun for decades. And that, of course, will stop photosynthesis, so all your plants die. You have the removal of the base of your food chains. All of the herbivores die. All of the carnivores that eat the herbivores die. So this is why this was such a destructive event. It wasn't just about the nearby consequences. We also have the vaporized rock, which would have given 5 to 10 years of sulfuric acid rain, as if things weren't bad enough. It would have destroyed the ozone layer very efficiently. Fortunately, if we're looking for good in this, you didn't need the ozone layer for a little while because the Earth is so covered in soot that the UV radiation couldn't come through. So, but those vaporized gases will have created a greenhouse warming effect for thousands of years. So you've just gone... The dinosaurs were used to warm conditions, and then they get plunged into decades-long nuclear winter. And then if you manage to survive because you're used to cold conditions, you've now got 5 degrees of warming for the next few thousand years because of the enhanced greenhouse effect. So, that was my main aim for the talk tonight. I enjoyed bigging up the Nadir impact crater, and its discovery is significant. And it did kill some dinosaurs. But Chicxulub was the global killer and could have done it itself. I do have my pop quiz question next. If you're a fast reader, you might get there before the rest of them. Okay, Tucson dinosaurs, a meteor has hit Flagstaff, and how is your day about to get worse? So what's your play order of bad events? A, earthquake, thermal pulse, air blast, ejecta. Or B, thermal pulse, earthquake, ejecta, air blast. C, air blast, ejecta, earthquake, thermal pulse. Or D, ejecta, air blast, thermal pulse, earthquake. Oh, yes. B, that's right. Brilliant. And I think that's... Yes. Thank you ever so much. It's been fun. Oh, yes, questions.
Obviously, this is going to be based on drilling into figuring out what's down there. Is there any way you could more accurately determine the ages of both those things? Determine maybe they were at the same time, maybe they're two pieces of the same rock that split apart in the crash? Like, can we get that close so that does well?
Excellent question. How accurately can we date this impact crater and the Chicxulub impact crater? So when we drill down into it, we're going to rely on getting some melt rocks. So finding rocks that were melted by the impact, and then their geologic clocks are reset when they solidify, and so that gives us their age. I believe the error on that is, I've heard 11,000 years, but I've also heard 1 million years, depending on. So unfortunately, I don't think we'll ever be able to prove. No, wait. We will never be able to prove whether this happened on the same day as the Chicxulub impact, but it's still significant even if it happened within 1 million years, because it takes a long time for the Earth to recover. So if you get hit with another asteroid while you're recovering, yeah, it's awful.
Where does the name That's the answer. There's always an Amtrak right all the time. Where does the name Nadir come from?
The name Nadir comes from the Nadir Seamount. There's a lot of volcanic activity south of the area that we were looking at, and the closest seamount, which is a volcanic feature, was called Nadir. So that's what we went with. Oh, and I found out Chicxulub means the devil's flea. Just trivia. Yes. Oh.
Have you been able to calculate the impact trajectory of those meteors?
So the question was whether we could calculate the impact trajectory. With Nadir, we're not at that stage yet, but with Chicxulub there's been a significant amount of work done trying to map the global ejecta. And if memory serves, they have worked out that it was an oblique impact, lower down than 45 degrees. So, and statistically, most impacts would be an average of 45 degrees. But as soon as you start to go lower than that, your ejecta that's thrown out isn't all the way around the crater. So we've started to use the ejecta patterns to get an idea. I think, I might be completely wrong on this, but I think it came in from the southeast.
Would an asteroid more perpendicular orbit cause way more devastation than like the oblique ones?
The question was roughly how much damage would be created by oblique impact craters, oblique impacts, versus straight down. You get a different distribution of your energy when you come in from the side. And it would actually, in the case of Chicxulub, it's predicted that it was more devastating because it came in at a steep trajectory, because more of the subsurface rock was vaporized, so that led to a lot more atmospheric gases. Great questions. This is great. Okay. Thanks ever so much.
Thank you so much. Wow, that was really cool. All right, well that's a wrap on SpaceDrafts 81. Woo! We will be back on November 15th, always the third Tuesday of every month, always here at 7:30. You can follow us on Twitter and Facebook to keep up with our events and get notified. You can also join our mailing list. It's bit.ly/SpaceDrafts mailing list to join our mailing list, and so you can get our announcements delivered to your inbox and keep up with what we're doing with our shows. And with that, don't forget to check out the telescopes. Don't forget to tip your bartenders. Don't forget to check out the merch. We also have a tip jar as well. And don't forget to come back on November 15th. See you then.